In advanced fluid mechanics, vector identities are not decorative mathematics. They are structural tools. They allow us to rewrite the governing equations in ways that reveal physical meaning. The goal of this video is not to prove identities formally. The goal is to become comfortable using them and to see why they matter in the context of fluid dynamics. We begin with the identity. The curl of a gradient is 0. Nabla cross nabla phi equals 0. Now apply this to the incompressible Navier-Stokes equation written in material derivative form. Density times the material derivative of velocity equals minus the gradient of pressure plus mu times the Laplacian of velocity. Take the curl of both sides. The curl of the gradient of pressure vanishes by the identity. Pressure disappears entirely. What remains leads to the vorticity equation. This shows something important. Pressure does not directly create vorticity. Vorticity evolves through convection and viscous diffusion. An identity has exposed structure. Next identity. The divergence of a curl is 0. Nabla dot nabla cross A equals 0. If vorticity is defined as nabla cross velocity, then its divergence is automatically 0. Vorticity has no classical sources in the flow field. Again, this is not abstract math. It constrains rotational motion. Now consider the divergence product rule. The divergence of phi times u equals phi times divergence of u plus u dot gradient phi. Apply this to the continuity equation written in conservative form. Partial rho with respect to time plus divergence of rho u equals 0. Expanding the divergence term gives partial rho with respect to time plus u dot gradient rho plus rho times divergence of u equals 0. The first two terms form the material derivative of density. This shows that the conservative and material forms of continuity are mathematically equivalent. There is one mass conservation law written in different forms. Now we move to a powerful identity for the convective term. U dot gradient u equals the gradient of 1/2 the velocity magnitude squared minus u cross vorticity. Here, we intentionally use the non-conservative form of Navier-Stokes, where density times partial velocity plus density times u dot gradient u equals minus gradient p plus mu Laplacian u. We choose this form because the identity applies directly to the convective term u dot gradient u. If we used the conservative form involving divergence of rho uu, the structure would look different. Substituting the identity, the convective term splits into a gradient term and a vorticity term. Grouping the gradients produces the gradient of pressure plus 1/2 rho velocity squared. This combination is often interpreted as total pressure. The remaining nonlinear term involves velocity crossed with vorticity. This shows that nonlinearity in fluid mechanics is tied to vorticity. If vorticity is 0, as in potential flow, that rotational term disappears. The identity reveals the path toward Bernoulli's equation. Next identity, the vector Laplacian identity. The Laplacian of a vector equals the gradient of divergence minus the curl of the curl. For incompressible flow, divergence of velocity is 0, so the Laplacian becomes minus the curl of vorticity. This shows that viscosity acts directly on vorticity. The viscous term is a diffusion mechanism for rotation. Finally, the dyadic divergence identity. The divergence of uu equals u dot gradient u plus u times divergence of u. For incompressible flow, divergence of u is 0, so the divergence of uu reduces exactly to the convective term. This explains why the conservative and non-conservative forms of Navier-Stokes are equivalent when continuity holds. Different textbooks emphasize different forms, especially theoretical texts versus computational fluid dynamics texts. The physics is the same. The identities connect the forms. The purpose of this video is not memorization. The purpose is fluency. In advanced fluid mechanics, we constantly reorganize equations. We eliminate pressure by taking curls. We reveal total pressure by regrouping gradients. We connect viscosity to vorticity through the Laplacian identity. These manipulations are only possible if we are comfortable with the identities. In the next videos, we will apply these tools directly to creeping flow, vortex dynamics, and potential flow. Master the identities and the governing equations become transparent.